doesn't exactly fit in the topic of the conference. Maybe it's something in between the G and the S. It's something that has to do a little bit with the gauge theory and string theory, as you will see in a moment. And it's a work basically that appeared, well, 1 month ago, maybe, or something, with Miguel Correa and Alessandro Giorgudis, which are depicted in this picture here. And, OK, let me start. So let me remind you a little bit what are the various regimes in QCD which we love and we are interested in. So we have like 2 Mandelstam invariants which control the scattering processes in QCD. And we have this beautiful triangle which summarizes them all. So on the top, you have the asymptotic freedom regime, which is also the one that is closer to the topic of this conference, where as the energy is very large, momentum transfer is very large, and we can use perturbative expansion, and we have a lot of tools. Then there is the regime in which S and T are order 1, where you have confinement, and where we have developed many techniques, like lattice QCD, now there is S-matrix bootstrap, and sometimes, since S and T are smaller than 4 pi something, you can think that it's small, and you can use some perturbation theory also. It's like a hard regime. But then there is in my opinion, the hardest regime of all, which is the one of four-dual scattering, or soft QCD regime, in which S is large, but T is small, order 1. And this is basically what I'm going to talk about. This will be the topic of my talk. So you see, it's like a little bit gauge, string, it's in the middle. Yes. OK, so the first and most important result in this regime that we can actually say it's rigorous from the quantum field theory point of view is the Froissart bound. And Froissart bound has something to do with the scattering of 2 particles. So you have 2 particles that go into 2 particles. You take the final momenta to be equal to the initial momenta. And then by the optical theorem, you all know that if I take the imaginary part of this process, this is proportional to the sum of the probabilities for 2 particles going into any number of particles. So it's like a bit far from integrability, but still. This is like what the imaginary part gives. And so you can already see that if you want to define the total cross-section, which sums up all the possible processes that can happen in a theory, you will have to take the imaginary part. And indeed, the total cross-section is just defined as the imaginary part at t equal to 0, because I set the initial particle, the final particle to be initial particle, so momentum transfer is 0. And you take the imaginary part, you divide by the flux of incident particle, and this beautiful bound that just depends on the axiom of quantum field theory tells you that this quantity, asymptotically when S goes to infinity, is smaller or equal than some log. So there is this log square, where the 2 is because we are in 4 dimensions. The 4 pi, you can define it in many different ways, but I like to think as the strong couplings in the effective field theory. And then there is a T0, which is a scale that gives the correct dimension to the cross-section. So it's a famous Froissart bound, which often people call it Froissart-Martin bound, because it was like rigorously proven by Martin years later using only the axiomatic framework of quantum field theory. And OK, this is like a beautiful result that stands since the 61. So in this talk, we basically challenge the result, and we try to go a little bit beyond, but this will come later. And T0, if you want, it's like 4m squared, which is the 2-particle threshold, if there are no spin-2 bound states around. OK, now let me remind you a little bit why Regge theory was so successful. So why like experimentally, basically successful. So you see, like this has something to do with the discovery of spin J particles. So if you have in a theory spin J that you can exchange spin J particles, then in the T channel, your amplitude will grow like S to the J. And this will immediately violate the Froissart bound that I just showed you. So the solution that was put forward by these people back in the days for the Regge theory was to take J and make it a function of T. So in this way, if J is a function of T, at T equal to 0, you can run it to a value which is compatible with Frost bound, and everything is fine. Okay, so you go to like S infinity fixed, and the amplitude behaves like this. And indeed, basically what Regge theory tells you is that this exponent is basically given by this Regge trajectory, where here you can put all the all the resonances in QCD on a line, and okay, it's almost a line. I think it's curved, but okay, it's like a line. And it has some intercept. And then you see that immediately the Regge theory would give you some prediction for how the amplitude should grow. And then basically the first result that make Regge theory successful was the fact that if you look at proton-proton, antiproton total cross-section, it decays a little bit. This is just because I'm reminding you the cross-section goes like alpha t minus 1. So if the intercept is 0.55, this thing should decay. So this was a success of Regge theory. But then, already in the 70s, people discovered that the total cross-section should actually grow. It grows slowly, but grows. And if it grows, then it means there must be some other trajectory dominating. And this is the Pomeron, what people named the Pomeron back in the days. No? So there's some Pomeron trajectory that should intercept around 1 here. But what are the evidences for the Pomeron? So one experimental evidence of the Pomeron is this concept that I didn't know about before starting this project, which is the shrinkage of the diffractive cone. They call it experimentalist. So it's just a simple fact. You plug S to the alpha of t into the differential cross-section formula. So d sigma elastic in the t, just the amplitude square divided by square, the symbol ratio. You plug this formula, and immediately you see that this behaves like an exponential of t. So shrinkage is because as a function of t, this cone just becomes, decays exponentially. And then as function of s also should shrink because there is some log dependence in this coefficient. And the rate at which it shrinks, it depends on the slope of the Pomeron trajectory. So this was like one sharp prediction of this picture. And then indeed, already long time ago, and then more recently, people saw this exponential decay in t, and they could even measure from this difference the alpha prime p, which suggests that indeed there is a flat trajectory that dominates this cross-section at high energy. And well, today, I mean, this is like some update. There are also like signs of deviations from this logarithmic shrinkage. So, and this is something that will come up later in the talk also. So, but this is like the experiment of the Pomeron. But when you look at this picture, at least when we started to look at this picture in detail, we saw that everything fit in a beautiful, let's say, logic. But actually, if you look at the details, there are some things that are still not satisfying from a theoretical point of view. And here I'm naming a few, which are the few that we could address in this work. So one thing is like maybe the most obvious, but still it's something not clear in the literature, is the tension between the Frost bound and this alpha p, which is 1.08. So there is number 1.08, but alpha 0 should be 1 according to Frost bound. So there is some tension. Then there is a clear experimental gap between the bound that, for instance, has been measured at LHC, which is like order 0.27 millibar, and actually the bound that you get from Frossard. There is this huge factor, so it's like a big difference. And then, more formally, the total cross-section at fixed S, if you maximize it, goes to infinity, because the amplitude is a distribution on the real axis, not a function. So it can diverge logarithmically, there is no problem with unitarity. And then there is some hidden result, actually, from Oeme, a theorem by Oeme already in the 70s, that says that the Frossard growth is incompatible with the linear trajectories. So if you trajectory with linear slope, this is incompatible with the log square. And this is like an old result. So you see, then you start to have claims like perhaps 14 TV is not asymptotic, perhaps Frossard band is not optimal, what is as not in the, in the normalization of the log, these formal people that care about distributions, who cares? And then OMA proposal, nobody knows what it is, but it was already proposed that like some square root of t, slope or something. So basically what I will do in this talk is to address these 4 points and try to make these blue statements a little bit more systematic. So this is the plan of the talk. Okay, so now let me give you some, basically already some summary of the main results that right way answer these questions, just to give you an idea. So one first main result is that, okay, we get rid of point like, we don't like distributions, we like functions, we like to smear distributions against some proper test functions, and we took this proposal already put forward in the 70s and revisited by Zibedov in the 2020s or something, and we basically, what we did, we took the absolute, well, the total cross-section, and we average it with some function. You can use many different functions with some, the shape of this kernel is for technical reasons. And we put an absolute bound, and this is what I will discuss in this talk, at each value of the energy. So it's a bound that you can take the experimental data, you can smear them too, and you can put these two plots on top of each other, and you can say, okay, this region here is clearly excluded. And this is something that has never done before. So we get this exclusion bound, which is analytic, actually. Well, it blends analytic and numerics, and I will show you in a few slides. And we could compare with proton-proton. But let me make a disclaimer, just for the, just to be fair, that I will consider only scattering of scalars. Protons are fermions, so they have spin. And I will assume that basically to make sense of this plot, you have to think that spin effects decouple at large energy, pion exchange perhaps is irrelevant. And if you believe all these things, then we get a bound which is order 10 from the proton-proton cross-section. Okay, so we got like instead of factor 100, a factor 10. But this you might complain because of all these assumptions. And then the other thing, of course, that we clearly see, because we have the analytic expression, we can see that the log square asymptotic is not reached at 14 TeV, basically. So it's clearly not asymptotic. So it's like just an outcome of this analysis. Then the second main result is that with the bootstrap, with the numerical bootstrap, we can reconstruct the function that we believe is the one that maximizes the interaction strength. And I will bring some argument, let's say, it's a conjecture, I don't have a proof, of course, that the amplitude that maximizes the interaction strength at basically at all scales sits at a special corner in a kink. And this kink is basically in the space of, let's say, the first two couplings that appear at lower energy in an amplitude, which is lambda phi to the 4 in a scalar amplitude, and d4 phi to the 4. So with the bootstrap, we have this allowed region, which is here. You have free theory down here. You have some special points. And the amplitude that we believe saturates the non-perturbative version of Frossard bound sits at this corner here. And you get this kind of shapes. So you see, it's like a very complex function, which has like peaks, dips, and different colors are the spin decomposition. So it's like a lot of structure that I won't discuss in detail. But this is the amplitude we construct. We call it the Frossard amplitude. And this will basically teach us something about this bound. In particular, that the black disk picture, which is the one that you imagine when you smash particle at high energy, is not the correct picture. There is another picture. So this will be the, this will be the result. Okay. So now let me explain you in 2 slides what is the asymmetric bootstrap. Maybe there are people that already know this, so sorry if I have to repeat myself, but let me give you a different perspective on the S-matrix bootstrap, which is that now we think of it as a more effective S-matrix approach, in a sense that what we do at the end of the day is that we construct the most general function satisfying analyticity, crossing, and unitarity. And this, if you think about it, it's not that crazy as an approach, because in effective field theory, this is very standard. In effective field theory, you write a Lagrangian, which is your tool to parameterize all possible interaction compatible with the symmetry. Then you use perturbation theory to get consistent answers. And in this effective S-matrix approach, we write an ansatz, and then we use optimization theory to get answers. So it's like a non-perturbative version of effective field theory that has like good and bad things. The bad thing is non-systematic, as you can imagine, because I write an ansatz, optimization theory, what it means. We also don't know what it means exactly. So it's not systematic. But it's hard to include multi-particle. unless like there was like a recent attempt by me, Alessandro, and Pedro recently, but there was basically no non-perturbative multi-particle bootstrap, so it's very hard. But the good thing is that no perturbative, so it's ideal for strongly coupled systems, QCD, and integrable models into dimensions, for instance. So that's why it's very good. Now, let me tell you how it works in one slide. So we call it, this is like the primal strategy. We have many different strategies because it's an optimization problem. We can solve it in many different ways, less or more rigorous. One strategy is the primal. So consider the theory of a gapped scalar in 4 dimensions with mass m equals to 1. Then what we do, 3 steps. One step is to construct an ansatz, which I should not call it ansatz. I should call it, we expand the amplitude in a basis of functions. It's a Taylor expansion in a polydisk in this variable rho s, rho t, rho u. And since this variable depends on st and u, and these coefficients are permutation invariant, then this function is automatically crossing symmetric, and I sum up to n, let's say n terms in this basis expansion. Then this rho map is given by this Joukowski function, which just maps the cut plane to the unit disk. And for instance, there is a parameter here which is not the same as not as the Frossard bounds, another as not. Some arbitrary parameter for this conformal mapping that maps this point to the center of the disk. The cut goes, let's say, the upper part of the cut to the upper circle. And this ensures maximal analyticity for the amplitude, in the sense that this function clearly has cuts for all st and u, and it's analytic away from these cuts. Then we have to, then this function is crossing an analytic, but it's not unitary. So what we need to do is that we need to project into partial wave. We have to diagonalize the angular momentum operator. So we go to partial wave, and then we just project the amplitude with some Legendre polynomial. And t, you make it a function of the scattering angle cos theta and the energy in the center of mass. There is some prefactor here, but it's like a partial S matrix. And then the third step, once you construct this linear functional of your ansatz, so you see one point to stress is that this function is linear in the alpha, this projection is linear, and therefore when we maximize any objective, which can be, for instance, the total cross-section or any observable you want, with these constraints that the probability is conserved, it is just quadratic. And it's a good thing because we can solve it using semi-definite programming. And what we do is that we relax in a 2x2 matrix, and then we impose this constraint. So you see, it's a constraint optimization problem. You maximize something given some constraints. And then we use a grid for any energy greater than the 2-particle threshold, and then for any spin. And then, of course, the tricky part, which is the one that I will put under the rug, is that we have to take limits. And it took us years to make this limit under control. It was not easy, but now we can take n to infinity reasonably, L to infinity much easier, and the grid we can make it very dense. So in this way, all these asymptotic limits that make sure that this function is very generic are satisfied. But this is like a numerical procedure that we have to follow. Okay, so this is the strategy for the bootstrap. And now, now let me go to the main goal of the talk, which is to bound the cross-section. So now the observable that I'm going to bound is the cross-section, but I will first discuss the analytic bound. Well, semi-analytic bound. So, yeah, I wrote it in d dimensions, it's not important. Put d equals to 4 here, it's fine. So we take this smeared cross-section that we want to bound at each s, where s is the extremum of integration. So we smear it from 4 up to s. I want to bound this function of s. The first step is very simple. We expand in partial waves, and then we split the sum. And this is the trick that has been used already in the past forever. So you basically expand. You expand in spin. There will be some, the S matrix will appear now in the expansion. And you have like low spin and high spin, and we want to bound separately low and high spin. Then for the low spin, we use unitarity. And unitarity just tells that 1 minus the real part of a probability is smaller or equal than 2. And we plug it here. And then if you plug it, you do this sum from 0 to L minus 2, you get some Pochhammer. And this gives you a bound on the low spin part. So it's just pure unitary, just bound smaller or equal than 2, which goes like L squared in equals to 4. But then the hard part is this high spin part. And for this, what we will do is that we will recast this asymptotic sum into a bound on some other observable. And this other observable, for some technical reason that I'm not going to explain, it's just the second derivative of the amplitude at some point. And this point, it's any point in the Euclidean region of the amplitude, so below threshold. Why this is nice? Because this quantity is dispersive, so it's this C2 that depends on some value of t of momentum transfer is given by an integral of the imaginary part, which is positive. Then you can expand also this integral, and you can basically put an inequality by restricting the integration range and by restricting the sum. So instead of start from 0, start from L, instead of integrate to infinity, you integrate up to S. This gives you an inequality that involves the sum of high spin times some trivial kernel, and we use basically the bound on this C2 to put a bound on this high spin part. That's it, use just an inequality. So all in all, what we get is that we get an analytic expression which is valid for any dimension, for any value of the spin and for any momentum transfer with arbitrary parameters. These are arbitrary parameters in principle, and depends on a data which you don't know how to bound analytically, but you have to bound numerically, and that's where we use the S matrix bootstrap. So we bound this C2 of T naught, and this is the results. So for instance, these are different values of n, the number of terms in the basis, and then you extrapolate n to infinity, you get the black curve, which is pretty close to the last point we have. So it's the maximum. You plug it here, and then you can minimize numerically with respect to spin and T naught. So you get the best bound. You can massage this expression, get something. So this is the result. And then one thing that you can do is that you can take S to infinity, and then you can check that if you take the saddle point, this expression becomes the Froissart bound in the dimensions, if you want. So it's like a consistency check. So this was the result that we obtained. And again, it's a bound on the smeared cross-section. It's valid at any energy, and it's rigorous, let's say. So let me go to the end of the talk already. So let me know what we did is that, we put analytic bound, and we checked that the analytic bound receives sizable correction 14 TeV, so we are not asymptotic at LHC. We put bound at any S on a properly smeared observable, but is it optimal? What about OM's theorem that I mentioned, the fact that the trajectory should have like square roots and not linear? These are the other questions. So let me say something about this. So about the optimality, what we did is that we maximized the smeared cross-section numerically this time. So before it was an analytic bound that used some numerical input. Now it's direct numerical optimization, which is super hard, because you have to do for each S. It's not analytic in S, the expression. And we get these points. We can extrapolate. So we get all this region is included. All this region was excluded. And the good news is that we get a factor 5 improvement. So now we are just a factor 2 from proton-proton scattering. So we did a lot of mileage. And it grows slightly with S. I mean, you can barely see here because it's very hard numeric, but OK, we believe it grows slightly with S. And then what we can do? Well, now what we can do is that for each value of S, so for each value of where we maximize the total cross-section, we can construct an amplitude that saturates this bound. And then you can ask, what is the limit when S goes to infinity of this sequence of function? Does it go to a crazy function? Is it a nice function? What it is? And this would correspond to the strongest interacting amplitude, because you are basically maximizing total cross-section smeared all the way to infinity. And the way we argue, well, various ways to argue it, but the way we argue is that we plot the S matrix data for each value of S, and we see the movie. And the movie suggests that it goes to the king. We have other reasons to say it, but well, this is like one piece of evidence that if you increase the value of S, or if you smear at higher energy, these points move to the king. So now let me make a jump. Let me just assume that this is the amplitude that saturates the growth at any S, and let me see what happens. So the first beautiful thing that we see is that we see a discrepancy with the black disk. Because I told you the model behind Froissart wants a black disk, But instead, if we go to the impact parameter, so this, if you want, it's like some, perfect. It's really some picture of the sky that basically black, it means just the light was transmitted, and white was just completely reflected. And this is a function of energy, a function of impact parameter. So you see that there is some localized structure. An impact parameter, right, it's like a circular thing, so this looks like a ring. So basically this makes our conjecture that actually the ring model is the one that rules all the cross sections. Okay, so it's like there's some ring, it's not the disk. So we call it white ring because it's white, it's not black. And one thing you can do is that you can take this model, which is very simple, 1 minus 2 theta, heaviside theta, in some region. You can plug it into impact parameter formula and get some expression which is difference of two Bessel functions. And now you can check whether this model, inspired by numerical bootstrap, matches the behavior of the diffractive cone that I mentioned at the beginning. So we have a white ring, we don't have a Pomeron. So we can basically do the following. We take our numerical bootstrap. Basically, this is the differential cross-section for the Frossard amplitude. So the amplitude we believe saturates the Frossard bound. It has some behavior. It looks like linear Pomeron for small t. So we are happy because it looks like this picture. It reminds us QCD. Of course, we are very far from QCD. But then the beautiful thing is that this white ring model predicts more than the linear Pomeron that just goes exponentially down. It predicts that there should be some rings, because it's like a Fraunhofer diffraction. There are like some peak and some rings. And indeed, our numerics, which doesn't know anything about rings and models, it's like numerical result, it has these rings and this fluctuation. And this function, the dotted function, is our prediction using this model. So this model seems to capture qualitative the features that you see non-perturbatively. And then, just to give you some formula and connect to the old OMA theorem, this white ring model, of course, is compatible with Froissart growth in the sense that sigma tot goes like 4 pi the external radius square. And if the external radius grows logarithmically, you get logarithmic square, so this is very simple. But then we can do the following. We can take, since we have an analytic expression, we can look for singularities, and we have this function that's like just a Bessel function when our model, when you go s goes to infinity. We take Sommerfeld-Watson, solve this equation, this integral is to be this function, and get that partial way for this model have a branch cut. So it's like a Regge branch cut, it's not a Regge pole. And so this is basically, if you expand close to small t, you get 1 plus square root of t. So this model is also satisfies the OMA theorem. So we are happy. And now, just before concluding, the last slide, let me show you the spectrum. So we have a function, analytic function. We can look at the spectrum, and we observe a lot of Regge trajectories. So this is like basically the full picture of the spectrum. So in 2 words, we see, for instance, on the right, you see what you would see the usual Regge trajectory in the Chou-Frauchi plot that look, well, they are like a bit square root log-like, but not really linear. But you have this trajectory on the right. And then surprisingly, you have also trajectory on the left. And you have many trajectories with infinite slope on the left, which is this OMA hallucination. And then you also have that there is a trajectory that has an intercept close to 1, again, not 1, so we don't really know what it means this, but looks like a Pomeron. And so this is basically the status. We have a function that achieves all these properties, and it is like a crazy spectrum which we don't understand yet what it means, if it's necessary or if it's just numerical coincidence. So to conclude, what we did is that put absolute bound on the cross-section at finite energy, then the amplitude achieves the maximal growth, we believe it's at a kink. And then the Frossard amplitude has this rich nonlinear spectrum that we don't know what it means if it's necessary. And in the future, we want to scatter fermions, say, because we saw that this ring structure that we see in our numerical games is some ring structure that you also see at LHC. So it's something also that proton-proton has to do, and we don't know why. They have to have these rings. And, I leave you with this quote from from Frauci, actually, that I find very instructive about linear and nonlinear trajectories. And I'll stop here.
Questions?
Hello. Very nice talk, Andrea. Thanks. I haven't looked in about 20 years in this FRASA picture, so I don't know what happened in the meantime. But at the time, so there was a sort of transition in what people in the particle data group were thinking is happening with the total cross section. So before about 2003, I think people were fitting so you showed the plot for the cross section that goes something like this. So they were fitting the first part with a small power law, S to the epsilon, that was called soft Pomeron. And then afterwards with the FRASA bound with a pi over m pi squared, which is 60 millibarns, the thing that truly appears in the FRASA Martin bound. However, afterwards, people started ignoring this, and they just started fitting with pi over m glue ball squared, which is much smaller, and then they would put S0 at the beginning instead of at the end. So let me see if I understood what you're saying, that you're saying that it's really pi over m pi squared, but moreover, you haven't reached the asymptotic limit yet until 14 TeV. Is that a fair statement?
Okay, I mean, okay, this is like, okay, thanks for the question. So let me clarify this. So we are not really doing proton-proton. So clearly we are doing some, right? So for us, there is no pi over m pion square. For us, there is pi over m proton square, like the global of the people. But, you know, we are, how to say, post-grip of physicists, in the sense that we believe the scale of QCD is lambda QCD, not pion. So what we would like to do in the future is to do the correct bootstrap, including the anomalous threshold from the pion, and check that indeed this at high energy, large impact parameter gives like a small contribution. So for us, you know, we have some belief, but no clear proof. So this is something we have to work on. And that, yeah, and then, this is basically the reason why our coefficient is much closer to the data than the naive bound where you put the mass of the pion. But this is the...
Yeah, what I was also wondering about the specific fit, because I don't know what happened in the meantime. But what I was confused at the time is why they changed to pi over m glue ball squared when they kept saying, oh, the fit is better, but it was actually 3% better in chi-squared. So I was like, well, that's not a good answer. So, so you would say that now the fit is much better in this?
No. I mean, from what we looked in some detail, and this fit is super hard. I have no idea how they managed to get like numbers. It's very hard. And what we see clearly here is that we have an analytic expression that we can compare with asymptotic expansion, and log square alone, it's far from being the only contribution at 14 TeV. That's what we observe. So doing these fits is an art, and yeah.
Okay. Good, I understand, thanks.
On the previous slide, is it possible to determine not Pomeron, but the Oderon trajectory?
Very good, yes, but not in this setup, because we have only identical scalars. So for the Oderon, we would need at least like non-identical scalars, at least. But that's something we want to do. It's in this scatter fermions or something closer to fermions outlook. But yeah, that would be amazing, actually, if you could see some Oderon emerging by unitarity.
Thank you.
There are a bit more naive questions. So how do you see all these rings from these deeps on your plot? What's going on?
How you see the ring?
Well, you always like ring, and then show some picture with a couple of...
No, but this is very hard. I mean, no, because you see, the ring is the impact parameter picture. So you have like some, you have like some impact parameter picture that suggests there is a ring. Then you check the consequences, and the ring describes qualitative, some differential cross-section and high energy. But then the range trajectories you are talking about are basically the peaks in this ring structure. And that we don't know how to, we actually don't know how to relate it to the ring, because the ring is very naive, doesn't have crossing. I mean, not even unitarity, it's really just impact parameter representation of some simple function. And we don't even have the nice square root branch part, because you see this trajectory curves but doesn't touch. And then on the left you have like many square root trajectories. So probably the ring itself, it captures some physics in some regime, but it's the correct picture that describes this amplitude is very different. And we should add more, we should have like some function that gives like more trajectories, more with the infinite slope, let's say. And this is something that actually, we only know one paper about this, which was by Schwarz before he moved to string theory. So we like to call them Schwarzian trajectories. So it's, someone thought about them.
So in this weird trajectories, is there any evidence or any, well, anything observed on these trajectories?
It's, we only have bootstrap, no, we have only have bootstrap evidence, because in all the non-perturbative amplitudes we construct, these trajectories seem to be there. So for us, it's a suggestion that perhaps are really something necessary for crossing. But it's non-perturbative, we don't know. Absorbing? Ah, observing. Ah, sorry, I thought absorbing. What are you going to absorb? No, no, and these are, no. These are impossible to observe directly. But many stuff are impossible to observe. I mean, you will be surprised how many things you cannot observe experimentally. I mean, let me give you just one, what is the plot? This one. You see, this is the total cross-section. So you have the peaks, that's the stuff you see. But then the other part on the subleading trajectories are these dips. So you will not going to see them if you just fit with Breit-Wigner. It's very hard.
Do you have some idea how this black ring picture could be explained from the old Parton picture? Do you have some physical idea what happens inside the hadrons?
Yeah, it's something that people are debating. Maybe I have some, let me go to the backup slides. Question. Yeah, so actually at proton-proton scattering, people observe something they call hollowness effect. They call this hollowness effect in the sense that the inelastic cross-section has a hollow, you see, has some small hollow at small impact parameter. So only like I have some image in which like you have this, basically these particles, if they smash up front, somehow they will just bounce back. Instead, if I smash them with some impact parameter, it's more likely they will fragment, let's say. But yeah, this is like people are trying to explain this kind of plots, and it's very hard. But they are trying with the Parton model, but I'm not an expert.
Okay, then I guess we need to finish. So let's thank Andrea
Thanks.
again.